We are going to be talking about easy DOE and in particular, the flexible mode. Now, I'm building on some recent DOE webcasts. Back in April, I did one on the guided mode. So that was easy DOE, guiding new users through designing and analyzing an experiment. I'm going to purposely not try to reproduce what's in that. So if you're new to easy DOE, I would recommend that you go look at this video and kind of then come back to what we're doing today. In addition, last month, there was an on-demand webinar series with 3 sessions, all of them great. But in particular, session 2 was also on easy DOE, and it was conducted by Peter Polito, another one of the systems engineers. And he did a design of experiments project with his family, building paper airplanes. And he's generously allowed that data set to be available and used. And so I'm going to base a lot of what I'm doing today on sort of leveraging some of the issues that came up along the way in his easy DOE and why we needed to go flexible, maybe to address some of them. So this outline, the first 2 are just one slide summaries, and then we will get into this review of guided easy DOE via the paper airplane report, and then have some discussion about real-world reasons why you might want to use easy DOE's flexible mode. And then the last part will just be dropping out to JMP and actually using flexible mode to address some of these issues. So why easy DOE? This slide is from Mark Bailey's webcast. The link is at the bottom. And this was one of the first easy DOE webcasts, and it was more about why did JMP create the easy DOE platform? We've had a custom DOE platform for years, and the reasons are listed here. We wanted this end-to-end coverage of every step. We wanted a streamlined experience, okay? We had a guided mode for novice experimenters, that's the default, and then I'm highlighting, today we're gonna talk about the flexible mode for more demanding situations. You do get a comprehensive summary report automatically written. You can save your work at any time and return to that same point, and easily share experiments with others, just like Peter is sharing his paper airplane experience with us. So why use DOE? Well, I've been using this slide for years. I hope everybody wants quicker answers, lower costs, solve bigger problems, give your management better information to make more informed decisions. We want to rapidly answer the what-if questions, identify important factors, do sensitivity and trade space analysis, optimize processes. And those 4 first bullets were covered in the guided easy DOE session that I gave last April. These next 2 bullets are really starting to get more into the custom DOE side of things, but you can be efficient by running, very important intelligent subsets of all the possible combinations so that for the same resources and constraints, you can solve bigger problems. And you can even run design sequentially. Not so much with easy DOE, but recognize that if you build an experiment, you could also add on to that without having to start over again to get a useful answer in even fewer trials. And recently we had a presentation by Phil Kay. He's a JMP, I'd call him a design of experiments evangelist. And he was talking about the benefits, and he kind of summarized it. Why would people use DOE? Predictability, productivity, and professional advancement. And people have lots of stories about advancement. The one I like to tell is years ago, I had a technician take a course from me on design of experiments, went back to his company, could not convince the 4 chemists that he worked for that they should do it, but he went off and did it anyway. And it wasn't very long before he became the manager and they laid off 2 of the chemists. So from a professional advancement point of view, he would tell you that DOE changed his career. So anyway, check out Phil's LinkedIn and blog posts on DOE. All right. Now we're going to get into looking at the guided DOE presentation. And one of the things that JMP now does is it creates a new file with a .jmp DOE extension. And that's the file you'll share to be able to share your results and your report with other people. So let's drop out to JMP and get that information. So I'm going to go over to JMP here and open up my paper airplanes average. That was the file that he mentioned. And you can see we've got our 6 tabs. I'll just click through them here once. And you'll notice we are in that guided mode at the top. Okay, so in this particular example, he was measuring. So the first thing he would have put in was his response, which was distance. So right here, you can see where he says distance. The goal was to maximize it. And all the way over here, he's even got the units in inches. Well, then he would have, besides responses, he would have entered his factors, and these would have been typed in. You'll notice one of them is continuous, and in his case, 3 of them were categorical. Okay, so they basically have 2 levels for each of those. The continuous one, if we ask for a response surface model, it'll use the low and the high, but it'll also give us a midpoint of that range. So these were the factors. Then you can either press the navigation control here or click the next tab. So either of these take us to the next step. I'll click the model tab at the top. And these are the default models. I go into pretty, not maybe extensive, but a good explanation on each of these. But the focus here is going to be on, we want to have prediction capability. And when you're looking for that, you're often thinking, I need a response surface design. And by default, JMP is saying we can do that with 18 experiments. So that's the number of runs here by default. The next step would have been to make that design. And I guess I'm actually computing a new one here, which may not be the best idea. But here is an 18 trial design. And just to make sure that everything's the same, I'm just going to reopen it so I don't create a new one. So let me reopen that file. Here we go. So I want to click this design. So I know this is the design that Peter saved. At that point, he could have clicked the export data and taken this table out and assigned, the pieces of paper and the type of paper and the width of the paper and the thrower, made their airplanes, ran the experiments, collected the data, and actually put the responses in here. And then at that point, they could have copied them, but they ultimately would have put them in here under the data entry. So here are his results, the distances in inches that those airplanes went. You always get this sort of factor plot down below. This is not fitting a model. This is just sort of connecting the means of the groups of data. Now, the 3 boxes on the right have categorical data. So it's, either one standard versus cardstock, et cetera. So we're looking at the average of those. The one on the left is a continuous factor. And so we could expect, if there was curvature, we might see that. By here, it would just be the points linking the means of the groups. So then we move on to the Analyze tab. And again, we can do that clicking down here. And in this case, the default saved analysis that he did was what's considered the best model. So he used this button. You'll notice we can also click Full Model. Okay, so Full Model has all of the terms that were in the model he chose for his design, which was the response surface model. So it was all the main effects, all the interactions, and in the case of the one continuous factor, we wanted a squared term. So you'll notice there is a paper length squared term in this model. And this is where things get a little interesting. You'll notice here that by this method here, it says all implied terms in the model are entered in green, but since 0 is the effect estimate is in every one of these confidence intervals, there's actually nothing statistically significant at this point. When you click Best Model, the red dotted lines are where we've zeroed out terms in the model. And now we've ended up with 4 factors that are significant. Okay, so they're the first 3, and then this one right here, you can see that the confidence intervals exclude 0. Okay, and then we have 2 that they're still here in green, so they're in the model, but they're not statistically significant, but they're close enough that they were being kept. And this whole topic here of what's significant, what's not, is what leads us to wanting to do something with the flexible mode where we're going to want to take more data. The next step is predict. This is that prediction profiler that you get in JMP. And so with this, you can interact with your model. You can see what effect the paper weight does. Here's the, with of the plane, whether it was an adult or a kid throwing it. And when the slopes change in other windows, that's because there's a term that allows for interactions to be measured. And then we have the continuous factor, which is we could have any piece of paper, between 5.5 and 11 here, and we've got a prediction for that. Well, all of this information gets rolled up into our report, which can be, if we click export here, we can either send it out as a PDF or as a rich text format. Or you can, if you have someone has JMP, you can just share the jump.doe file. But it records all of the results along the way, and even whatever your final prediction profiler was. So that was the example of a guided DOE using Peter's paper airplane data. Then let's move on to sort of the issues here. We've gone through the review of a guided DOE, and I pointed out this issue about sort of nothing being significant if we have the full model. And I really consider this a DOE learning opportunity worth discussing here today. When we click best model, we have 4 terms significant, albeit barely, meaning those confidence intervals just exclude 0, 2 nearly significant, and 5 have been set to 0. So to discuss this a little more, I want to show what happens if I just arbitrarily took the original data, copied and pasted it a second time, and then copy and pasted the first. There were 18 experiments, so either 18, 36, or 72, and reanalyzed, okay? And this is an example of there's a poor signal-to-noise ratio. The noise is what it is. This is what happens with you make paper airplanes and you and your kids throw them. There's just going to be a certain amount of noise in the process. And there's not a lot you can often do about that. And the signals get adjusted by, well, how much are we changing the factors? So how big is the difference between wide and narrow? How big is the difference between, light paper and heavy paper and the throwers? And I want to point out that there's a really big difference between saying, there's nothing significant here, let's move on, versus given the amount of data collected, we did not detect any significant effects. And so this is just illustrating if I increase the amount of data, I shrink the confidence intervals. And now as a result of that, we're getting more and more effects significant as I increase the amount of data that I take. And so one of the reasons that sometimes design of experiments fail is people have inadequately understood the signal to noise in their process. And so sometimes it's people are too timid with the variables. If you don't turn a knob very much, you don't make a very big effect. Sometimes people aren't aware of how much variability there is in a process. And you'll know this from different industries. You'll see people that do, tensile strength measurements. They always do sets of 3 or sets of 5 when they do these pull strength tests, because they know there's a lot of noise in the measurement in that system. Okay, so this is an example where one of the solutions would be, let's take more data. Now, again, just to illustrate, as I take more data and reanalyze it, you'll notice the predictions are exactly the same because I'm using exactly the same model and I just copied and pasted the data 2 and 4 times, okay? And as a result, you get exactly the same prediction, but you'll notice the confidence interval shrinking, okay, even on our prediction. So again, that's why we often want to take more data. Now, I do want to put a cautionary slide up here. I am just illustrating here when I copied and pasted the data the extra times as to what the impact of if we had more data would be. I am by no means suggesting you improve your results by falsely enriching your data. That was just more of a pedagogical thing here so that we can see the impact of what would have happened had we taken more data. Okay, inspired by Peter's paper airplane results, okay, let's build on it and leverage the flexible mode to address some of these real world issues. The one I've been really harping on here for the last couple of minutes is we need more data if we want to get more significance on the effects. So we're going to want to build a new design, but we're going to want to increase the number of trials. Okay, often you cannot shrink the noise, but you can shrink confidence intervals by taking more data. And we're going to see that when we make designs, we get to choose among the number of unique trials, the number of replicates, the number of center points, and the block size. So this is what flexible mode is going to now offer to us that the guided mode really only offered us the total number of trials. I'm also going to make the problem a little more maybe not difficult, but more complex by adding some more factors. Okay, now we're going to have a couple of continuous, one discrete numeric at 4 levels, one easy to change categorical factor at 3 levels, and one hard to change factor at 2 levels. And as soon as you put a hard to change factor in, you will trigger the flexible mode, because that is the only way that you can handle that kind of factor in the easy DOE platform. We're also going to look at some things under the analysis under flexible mode, and that's where we're going to be using the generalized regression platform. And there are some advanced controls there where we can do things like enforce heredity or force particular terms into the model. We can also use non-normal distributions. We're not going to spend a lot of time on the GenReg platform, but these are the kinds of things that we can do in the flexible mode with JMP. So to highlight the difference between the flexible mode on the left and the custom DOE platform on the right, you can see that the design generation part is identical. Okay, there are a couple of things, several things that don't show up in the flexible mode. Things like defining factor constraints, you're going to have to use custom DOE for that. If you want to use Design Explorer, you're going to need custom DOE for that. If you want covariates and candidate runs, you're going to have to use custom DOE for that. But the main thing you're going to have here are the ability to change the size of the blocks that you might want to run, the number of center points, the number of replicate runs, and down here, if you choose user specify, you can change that number. So that's where we'll be headed. And when it comes to the GenReg side of things, I'm just going to say that the safest thing here is to say that the default settings are robust, and it's unrealistic to explain all the features, options, and statistics behind the choices in a couple of minutes. I would strongly recommend you look at Clay Barker, who's the main developer of the generalized regression platform. He has 3 developer tutorials. Each of these is over an hour long. And the main one to look at is the first one, which is addressing designed experiments. But you can also use GenReg to look at observational data, as well as to choose what type of distribution makes sense for your response. So I'm not going that deep today, but there are resources to get there. So when do we use flexible mode? From a design point of view, it's when we want to adjust the number of blocks and how big the block sizes are. If we want to adjust the number of center points, the number of replicates, the overall number of runs, and when we have factors that are hard to change. When you want to control fitting of the model, here's where I would say the settings that are there are pretty robust. There's not a lot of reason to want something other than best subset. I will show some reasons you might want to go into the advanced controls. We usually start out thinking data is normal, but it's not always normal. And if it's not, you can change the type of distribution. With small data sets, the best validation method is typically the AICC. That small c on the end stands for correction for small sample size. So again, typically you won't want to change that. And then if you do make multiple models, you might want to compare fit. So there's kind of 5 reasons for flexible mode on the design side of things and on the fitting of the model side of things. And we'll get to showing each of those in a few minutes here. So for the paper airplane, on the design side, what we're interested in is we might want to change the number of blocks. If Peter's family did 18 runs on one day and they said, nothing significant, let's just go do it again tomorrow. Well, tomorrow, did the wind shift? Are they better at throwing planes because there's a learning curve? Are their arms sore from yesterday? Is today hot and dry and yesterday cool and damp? Is there an unknown factor that they're not even taking into consideration? Could it be combinations of the above? For all of these reasons, if you add a blocking factor, you'll at least be able to detect if there's a statistical difference between yesterday's data and today's. Ideally, we hope that it's not significant and we kind of breathe a sigh of relief. If it is significant, it really means we've got detective work to do, because you don't know if it's the wind shift, the learning curve, the sore arms, etc. All you know is something completely correlated with yesterday's data and correlated with today's data is different. So we need to figure what that is. We really aren't going to deal much with center points because most of the factors were categorical and there was really only a midpoint on one continuous factor, the length. Replicates, though, this is where, because there were barely any significant effects, we do want to increase the number of trials so that we can shrink those confidence intervals. Remember, we can't change the noise, but we can change the confidence intervals by taking more data. And so again, from a number of runs point of view, we can increase the number of unique settings. And it turns out the optimum setting was missing. What I'm getting at there is there were only 24 possible combinations of the factors that Peter used. And turns out the one that was supposedly the best was missing from their design. So in forcing the number of unique runs, we could actually make sure that that optimum setting is in the design. And then finally, the one that we're going to introduce is this new hard to change factor. Okay, maybe I'll come back to the fitting side of things. So this is sort of DOE paper airplane 1.1. We're switching to flexible mode for Peter's example. Got the same response, we've got the same factors, we've got the same ranges and levels. They're all easy to change. We still want to support a response surface model. The big difference is right here, we start talking about we need more data. We know that we didn't have enough. So if we're going to do it again, let's take more. And if we ask for 36, we know there's going to be replicas because there's really only about 24 combinations of 2 by 2 by 2 by 3. Okay, again, we could look at this. If we think the data are not normal, we might want to use, hey, a log normal distribution. And then we could also try to force all the main effects into the model. It turned out not all the main effects were in the result of pressing best model. So those are things to do in this reboot of this example. So what we're going to do is bring up the factors and load them, and then switch to flexible mode where we'll see this design generation platform, sub-platform in it. And that's where we can adjust the blocks, the center points, the replicate runs, and the user specified. So let's go open paper airplane .jump DOE and save the factors for this new DOE. So we're back out here. This is that paper airplane file. And so the first thing maybe we could address here, just to take care of it, is under this analyze platform, is if we now switch it to flexible mode, all of a sudden we see this generalized regression platform showing up. Okay, this is, again, I don't really want to get into explaining all the details here, but I do want to show you what you could adjust. And one of those things here is you have this model launch. So if you relaunch, here's where you could change the type of distribution. You can also change the estimation method, although I'm going to say best subset is still probably what you want. You can change the validation method, but again, AICC is probably what you want. The one thing I will point out here is under these advanced controls, you can see there's an option for enforcing heredity, which some people would choose to check. And the other is you can force terms in. So if I come down here and click the 4 main effects, I am saying absolutely put those in my model. I want to make sure they're in there. So if I were to rerun this analysis now, and now go up to the top of this under model comparison, you can see that the first one was that sort of best subset by default, okay? And then the next one is a best subset where I forced in the main effects. And here you can see that the AIC is slightly better. Here, that's one criteria that people use when choosing models. But the other is the R-square here is better when I force things in. So you can, in this platform, ask to see the profilers. So if you hit the hotspot here and hit the control key and say profiler. And so there's the profiler for the top case, and there's the profiler for the second case where I've forced in the effects for all the main effects for all the factors. So at this point, that's an example of using the flexible mode to make some adjustments in this particular platform. The other adjustment we might have made, model launch, I might have also come in here and said, maybe these data aren't normal, and I might want to use something like log normal. And where the reason there's a hint for this is, if you were to look at the predictions and you went to very low predictions for distance, The closer you get to 0, let's just say the distance is 10 inches that the plane's going to go. Well, if the standard deviation for the full data set, I'll just say, was 50 inches, when you're throwing something that's going to go 10 inches, you really don't expect it to go plus or minus 50. So what you'll find is the standard deviation is shrinking as you go to small distances, and it's getting larger at large distances. And that's something that the normal distribution won't support, but a log normal would. So that might be a reason why you would use that. So if you click go here, now you get a third analysis. And if we come back up to the top under model comparison, you can again sort of start comparing things here and what modifications you might or might not make. Okay, I think that's as far as I want to go with the analysis platform, and I want to go back to the design platform. So let's go all the way back to the define stage where I've got the factors. And one of the options I'm going to do here is save the factors out. Okay, so we'll just call this, we'll give it a name here, save it as DOE airplane 1-1 there, and save. Try and save it there. Okay, so now I've got this file open. So if I get this old DOE out of the way, now what we can do is I go into Easy DOE, and rather than type all that in, I'll just say load the factors. And because that's the currently open data table, it just pulled that information in. It knew which ones were continuous, which were categorical, which were easy, etc., and had all the ranges. I still need to put that response in because I didn't save that, but that was distance. And I could put the units over here. He had that. Okay, so I've got my responses, I've got my factors, and now again, you can either hit the navigation control at the bottom or this model button at the top. And if we do that, we're still in guided mode, and we just get that choice of 18. But if we now switch to flexible mode, now we get the custom design platform, and we'll notice that the default model is just the main effects. We want the response surface model, so we'll click this button, which then adds all the main effects, all the two-way interactions, and the squared term for plane length. And in so doing, you can see that, again, the default is going to be 18. But here's where, because of Peter's experiment, and we had the luxury of looking at the results, we know if we're going to redo this, we want more data. So now we've got several options for getting more data. One would be, since if we wanted to sort of do the experiment over 2 days, I could click this group runs into block sizes of 18. And then under user specified down here, put 36. And what if I now make this design? I can either click the design button or the navigation control. Okay, so that took about 10 seconds, but now you can see that we have 2 blocks. You know, beginning at trial 19 is the beginning of block 2. And so we now have twice as much data. We'll have a higher probability of detecting effects for all other factors being the same. And we've built in the ability to test if there's a shift between day 1 and day 2. Doesn't tell us the cause of the shift, but at least if it occurred, we would know that it had happened. So that's one design change under the flexible mode. So I'm going to go back and I'm going to uncheck the block size here. This 2 doesn't really matter. And let's look at, I'm going to skip center points because again, there's just really not that many center points here, but let's change, say, the number of replicates. If I wanted to have 12 replicates, I can ask for that here. Once again, if I want the total to be 36, I would change that here. But now when I make this design, if I want to do a quick check on where my replicates are, what we'll do is we'll export the data. And now in this table, if I highlight, wasn't expecting blocking to be turned on. I must have had that checked. We'll just ignore blocking for a minute. If I had these 4 columns and I wanted to know, are there any duplicates in it? All I have to do is use the rows function, row selection and say, show me all the duplicate rows. And you can see there are 12 replicates in this data set. So the second occurrence or higher of any of these factors is highlighted here. So if you wanted to hide and exclude those, now what you've got are there are 24 combinations left that are not replicates. And that should be no surprise, given that there's 2 by 2 by 2 by 3 combinations of things. That's exactly 24. So that's an example of making the design where we forced in 12 replicates, and we got every trial at least once. So again, we'll go back. Yes, I realized I had not unchecked that. So maybe the last thing here would be if we set the replicates to 0 and we again ask for 36, what's going to happen here? Well, I'll make this design, and I'm not asking for blocks this time. Okay, again, I'll export it because that's a quick way for me to be able to use my look for replicates in this. And guess what? There's 12 replicates in it. And again, this gets back to there are only 24 possible combinations. And so it picked all 24, and then it picked half of them again, got chosen twice. Okay, so had I asked for larger numbers of replicates or larger numbers of unique trials, we know that pretty soon almost everything would have to be replicated. I think that's enough with reproducing the designs and the analysis with Peter's original work, and we'll look at maybe a slightly more complex example. Now we're going to go to, I'm calling it DOE Paper Airplane 2.0, because we've added the plane width now as a continuous response, and I'm giving it as a proportion of length. I've added the weight of the paper, so not just sort of normal and card stock. I've actually got 20 pound, 24 pound, 28, 32 pound paper, and I want those specific weight papers, and that's where we're using discrete numeric. So it models like a continuous factor, but it kind of designs like categorical because it's got to be just those settings. Now, in practice, a smarter way we already learned from Peter's example, if he used cardstock, I think that's up around 60 pound paper. If that wasn't a very important factor between 20 and 60 pound, I might have real trouble distinguishing between 20, 24, 28, and 32, unless I take lots of data. Then I can detect tiny differences. So just keep that in mind. From the thrower point of view, I decided to add, from my family's point of view, I have a son named Sam and a father-in-law named Sam, and I'll call one a senior and one a child. But if we were to do the experiment, one of the things is I've added a launch site. If I have a backyard with a high deck, I can either launch it at the yard level or I can launch it from the deck level. But in order to do that in a random fashion, we've got to run up and down those stairs. And if I'm going to do 36 of these launches, maybe someone would say, why don't we just do all the stuff from the deck at the same time and all the stuff at the yard at the same time so we're not running up and down? That would be a lot easier to do. Well, what you've just done is unrandomized that factor. And so that's what's called a hard to change factor. As soon as we add that, we have to be in flexible mode. A lot of the rest of this is the same. We want a total of 36. But the one difference is instead of there being only about 24 combinations, now there's really about 216 combinations. So the chances of us having everything are pretty slim here. Let's go out and I'll load the factors. I have them preloaded here. I'll bring in a file like that. And we're going to, because of the hard to change factor, we're going to actually see that the block size, center points, and replicate input boxes will disappear, and something new will show up called the number of whole plots. And we'll be able to adjust that. The default will be 4. I'm going to show it with 6, and I think I actually did it with 4, 6, and 9 to just sort of show here are 3 designs, but the hard to change factor is done in groups of 9 or groups of 6 or groups of 4. So let's go do this. So I'm going to use this factors for DOE 2.0 that I have saved. And you'll notice it's got 4 levels for the weight of the paper, 3 for the throwers, 2 for the launch site. And this is where when you save factors out, if I go to column properties for this, Let's do it this way. You can even see that the factor changes hard information is saved here. And so for that reason, if this is the active window and I go to any of the DOE platforms and choose load factors, it uses that file. And in this case, it says, guess what? One or more of the factor roles is not compatible with guided mode. So either had I had flexible mode up here chosen ahead of time, it would have all come in, but you'll notice the launch site did not come in. So if I change this to flexible mode and now reload the factors, it brought in that hard to change one at the bottom here, which is we're launching from the yard or the deck. Okay, again, we would want to put in distance as our response. And now we would move on to making our design. So again, we can click the navigation control. It brings us to the custom DOE platform. It seems to remember, no, it doesn't remember. It says there are currently 7 terms in the model. That's all the main effects for these factors. And we want a response surface model. So we'll want to click this button here. And when we do that, the 7 goes up to 23. So there's now 23 terms in the model. And by default, the minimum number of whole plots or groups of hard to change factors all at the same setting is 4. I'm going to make my father-in-law go up and down the steps 2 extra times here, or 1 extra time anyway. I'm going to change it to number of whole plots. I want my total again to be 36 because I know I need about that many to have things be significant. And if that's all set, you'll notice we've got 2 continuous, 1 discrete numeric, 2 categorical, 1 of which is hard to change. And therefore, we've got our 6 whole plots, and we'll make that design. Took a little longer, much bigger candidate set to choose from. But here's the end result. Again, I'll export it so that I can easily look at it. And so, you know, here are those separate whole plots. And if you use these histograms at the very top, it allows me to just kind of select it up here. And I was able to select out the sets here. So you'll notice we're in the yard, we're up on the deck, we're in the yard, we're up on the deck, we're in the yard, we're up on the deck. So it took 3 times going up the stairs, but we did all of these launches, and it's randomized within each of those whole plots with the different lengths, widths, and heights. Now, one of the things that occurs here that is troublesome to some people, you'll notice right here, there's a 9.625. In other words, I don't have just a low, middle, and high length. And I actually have a couple of intermediate levels for paper width here. And so those are occurring because the factors are continuous, and the algorithm that's trying to make the design is trying to minimize the prediction variance within the space. And so since it thinks those factors are continuous and you can make anything within that range, it suggests that these intermediate levels would be valuable for getting information. You might look at that as, oh, that's a pain. Now they got to measure out a bunch of different sizes here. I would have loved to have my whole experiment just be just 3 levels for length and 3 levels for width. And so the fix for that, I've got another set of factors that I've saved, only in this case, I made the length and the width also discrete numeric. So if I go to Easy DOE and I load this factor set, you'll notice, besides also reminding me, unless I put it in flexible mode, I don't get the hard to change factor. There it is. But because these are now discrete numeric here for length and width, these are the only 3 lengths of paper and proportion of width that I allow. So if I made this design, I would get out of design, and rather than take the time for that, I'll just finish it up with a slide of that. You'll notice here on the left is if I treat those 2 factors as continuous, I get these intermediate levels to the low, middle, and high. Whereas on the right, I sort of forced it to just have a low, a middle, and a high. So you can do all of that in the flexible DOE platform. So kind of my summary for today, when would you use the flexible mode? From the design side, if you find yourself wanting to run blocks, if you need to adjust center points or replicates, the total numbers of runs, or if you have a hard to change factor. On the modeling side, generally, I'm going to say things are going to work pretty well for you. I wouldn't change best subset, wouldn't change AICC, might under advanced controls force in main effects, might under distribution change it from normal. I would say you're probably not as likely to need to do that.